can I show you something? I'm working on basically the time traveling debugger for Python. That's what I'm working on. And I'll show you an example of what I got so far. I was starting the work on storing it in a SQLite database, but haven't finished that part. But let's take, whoops. Am I in the C Python project? Yeah, I'm in the C. So Python has a compiler and an interpreter. Both of them are written in C. And in the last week or so, I've really dug into the source code of Python, and I'm able to build Python. I type make here, and it'll build the C files, etc. And now I have a Python executable. It's called python.exe. Even though I'm on Mac, they call it python.exe, which is weird. And I have some test scripts. Let's do this permutations. So, okay. I'm gonna show you one of the programs that I have as test programs. So this is a test program.
Okay. Great.
And this is a problem that I solved for a LeetCode.com code challenge, and I just took that and put it in here as one of the test programs.
Sure.
And I basically hacked the code. I added a rewind module. Yeah. I think I'm calling this rewind, as in it's able to rewind your code. I added this module with a bunch of functions that are called whenever specific things in the interpreter happen. And then the interpreter code is in this file called ceval.c, and this file is where Python is actually executing the instructions line by line. It's executing something called bytecode, and the way it works is you take some Python code. I'll call it .py. Something.py. It goes to the compiler. I'm gonna use different shapes. Okay, something.py goes to the Python compiler. You don't think of Python as a compiler because you think of it as a interpreter usually. But the reason the reason there's a compiler is because there's a process to first take your source code and generate bytecode. Generate Python bytecode, which I'm gonna call PYC. Python compiled code, and that compiled code is in a binary format. It's difficult to read if you try to open up the file, but it's basically a to give you an intuition is like if you had a compound statement that's like let's say you had a statement like this, then the bytecode for that would be something like, load B, load C, add, and then load D, and then add, and then store it into A. So bytecode looks like this basically, where even if you have a compound statement, it breaks it down into the individual operations that would have to happen. So and each individual operation is like it's atomic operation. There's no compound. Even though you can do a lot in a one-liner, when it's converted to bytecode, it's the individual direction. Each instruction just does one thing.
So is this code directly like readable by the machine, or like
no? This is like this is a specific instruction set that Python defined specifically for Python.
Okay.
So this is not a real machine code, even though this look in terms of flavor, it looks a little bit like machine code, but it's not real machine code.
Gotcha.
Which is why we call it the Python compile code, and then that goes to the interpreter. That goes to the Python interpreter, and then out comes the result. Whether you print stuff out to the terminal or you have a web application or whatever, that depends on what the code actually does in this compiled code. So anyway, this c eval.c file here is the interpreter. This is the interpreter. So I hacked into the interpreter while it's going through each of the instructions, and I wanted to intercept. I want to intercept everything that Python is doing, basically, as it's doing it.
Okay, so how did you get the interpreter code?
I downloaded from their GitHub.
Oh, okay.
So Python,
right, so
Python,
code and then modify the code. Gotcha.
It's this one. It's Python/CPython. That's where their code is, and so I git cloned it, and then here I have their interpreter code, and it took some digging, and also asking the IRC channel where there's people that talk about Python there. I could go and ask question. I would have to say Python is pretty well documented. It is still difficult to learn it because there's just a lot there, but it's quite well documented. Like, it has these paragraphs here that you can read, and it also has links to other articles that you can read. But anyway, so this is where the individual instructions actually happen. There's a huge switch statement, and each target, each one of this target and then this name, that's the name of a type of bytecode instruction. No op means there's nothing to do. It's a skip. Load fast means load a local variable. There's a slow version of load, but loading local variables is fast. And then load const, there's like a const, like a number or something that you're loading. Anyway, so I can just see every instruction that Python does. I added this line here, which I call log op. I'm logging this operation.
Okay.
So I'm logging all the things that Python is doing, and in addition, I also do for specific things. I have an extra log statement, like list append. I want to intercept that in a specific way. So I have I added my rewind. Anything you see that starts with rewind, that's my module, right?
Gotcha.
And so whenever there's a list append instruction, I log that specifically, and also for the set add. There's a bunch of stuff. That store subscript is something like I have a dictionary, and then I do something like this. I'm storing a thing via a subscript notation. So this is store subscript. So whenever you do this in your program, it goes to here, and then I log that as well. So basically, I am intercepting all of these things that Python does, and I'm logging it to a file. So I just ran this program, right? So by running this program, it's gonna log this file, which I call it rewind.log, and it prints out this stuff.
Okay. What are the numbers? Like number 76. What is that?
These are line numbers.
Okay.
But this is not. This is some code in Python internals. So I'm gonna skip this part.
Okay.
The part that starts being our code is here. Here, that's the file that I actually executed. This one, right? And so I intercepted push frame, which is whenever a function is called, I push a frame onto the stack. So I intercepted that, so I print that out into this file whenever that happens. And here we are pushing frame where the source file is our permutations to source file. So here, and let me do this side by side. Okay. So this is line 1. It's over here, and we're pushing a frame because when you declare a class, you push a frame. and then inside the class, well, here it's doing some stuff to declare this class, I believe. Yeah, it's saying I'm gonna make a string whose value is solution, and I'm gonna store the qualified name of this class to be this string, and this string has this ID. So this star ID is referencing this string that has solution in it.
So is this code? So basically, intercept in the C eval, and then whatever the class you have a class, you declare a class, like all these just happen because you probably have intercept code of, say, like set up a class or whatever.
Yeah, I because I see all the. Actually, let me uncomment one thing in my code, and that will give you even more output in this file. So I'm gonna make. I uncommented these 2 lines, which give additional output. So I'm recompiling Python, and then I'm run it again. That way you can see even more of what's going on. Wow, it's taking a while this time. Okay, what did I change? That's fine. Okay, done. Okay, so alright, so now my rewind.log has a lot more stuff in it. I put these dash to mean like this is comments, sort of like. This is additional information in addition to the stuff I really want to spit out. There's a Python. The Python interpreter has a stack. Although this stack is not totally the same as the call stack, it's like the value stack. All the instructions like add or even call a function are based on what values are on the stack right now. But let's go to this file. I'm just gonna let's just skip to line 21 here in this file. So I'm gonna search for pound21. So okay. So this is store name permute unique. That basically means it has created this function, and it's gonna, here it says new object function here. That means it's created this new function, or my logging system has registered that the system created this function, and we're storing that into the name permute unique, which is what happens when you define a function, right? You store a function into some variable name. So that happens here. And then we visit line 21 over here.
Okay.
So let's try to follow what's going to happen. So line 21 is we're gonna let's see. We're actually calling a function here. So there's a call function instruction. There's a load name first. It's probably just to load the name solution here, because when you call a function, you name the function by name, so it loads the name of the function, and then it actually calls this function. And then when it calls the function, this class doesn't have a constructor, so we don't have to call the constructor actually. So there's no additional stuff here. And then we just end up with a new object of type solution, and then we store it in this s variable here. Okay, so that's line 21, and then we move on to line 22. Here we're gonna load this method, and and then my system has picked up that there's this new list. We created this new list with a 1, 2, 3 in it. So my logging system picked up, oh, there's a new list. And the way Python sometimes instantiates a list is first create a new empty list, and then it'll extend the list with these literal values in it. So we first get a new list, and then get a list extend with the 1, 2, 3 into the list.
That's pretty interesting. Like basically like walking through the code just by reading the.
Yeah, just by reading this log. Or basically you are tracing what the interpreter is doing step by step. And then we push frame, and that's the call into this method now when we push frame. So there's a name of the function that's being called, which is this permute unique method.
Right.
And then let's go now we visit line number 3. So let's go to line number 3. Line number 3 is this line, which makes sense because we just called that method. And then now it's gonna call this function. So we are let's see. We picked up there's a new list being created. That's probably this one here.
List.
Yep. And then we this load global load fast. Oh, we call this built-in function sorted. There it is. We're sorting these numbers. So we called this built-in function called sorted. My logging isn't.
So the stuff after the new list, like line 569, until you call sorted, what are those stuff?
What's sorted? Or...
No, so this line number 3 are basically to call permute unique with 2 variables. One is the empty list, and one is whatever the result you call sorted.
Yep.
So like on the right hand side, you have the rewind and the line between.
You broke off. Hello? Hello? I can't hear you anymore. Hello? Uh-oh. I'm not hearing you anymore. What can we try here? Oh! Wait. Oh! Sorry, 1 second. It might be a problem on my end. One second. Because you're interfering with my speaker. Can you hear me?
Do you hear me?
Yeah. Okay, we're back. Sorry about that. Okay. Let's continue. So these two guys get called, and then your question was what? Or these
like
these
the
guys?
lines between line 75 on the right hand side, there are a few lines between like create a new list and call built-in function, right? If you scroll up a little bit.
Yeah. Yeah. What are these doing here?
Yeah, like what are those doing?
Okay.
Here.
I think this load global again. It's just load this global variable, which is this sorted function, and then load fast is it's just loading this nums variable, loading its value onto the stack. Oh, and by the way, this stack, I should talk about this stack. This is like the working stack of the interpreter, and I just printed out here. So at the moment, the stack has a list and this function on it. And this function is called permute unique. So we're planning to call this function on line 6 over here, I think. And then when we load the global, you can see after loading the global, the stack now has this built-in function or method called sorted. So the purpose of the load is just to load the actual function in by the name of the function.
Gotcha. Okay.
And then load fast here is to just load the value of nums into the stack. So we have the name nums, we're just loading it onto the stack. And now after that, the stack has this list object on it.
Okay.
And then now we're ready to call this sorted function. So we call that. And the reason we had this permute unique function loaded onto the stack is because we loaded global for the name of the function initially. So we first load the function onto the stack, and then we need to prepare all the arguments of the function and also load them onto the stack. But because
stack is what are the stuff that you're currently working with?
Yeah.
In this is a function and a bunch of arguments. Okay.
Yeah. So yep, the stack is how it remembers its place. So after loading this permute unique function onto the stack, and then it's preparing the arguments it's going to pass to the function, which are first this empty list. So we did this new list thing, and now this is a new empty list. It put that onto the stack. And then to prepare the next argument to the function, it actually has to load another function and call it, right? So that's what it was doing. Loaded the sorted function, and then it also had to load this list, which is the argument that goes into sorted. So it did that, and then I called sorted, and then as a result of calling sorted, it's got another list that's in the stack now. That's the result of whatever sorted returned. And then now we finally push frame to call this permute unique function, and then we keep going. And now we're on line 7 now.
Okay.
Yep. So yeah. So well, let's not. Well, there's a lot of content here, so we're only about like 1/5 of the way through the execution of this program, but and this I don't. Well, this is gonna find all unique permutations of the numbers 1, 2, and 3. So it's gonna keep looping here for a while. But essentially, my goal here is to track everything that happens in the program to enough detail that I can write another program that reads in this log and reconstruct all of the previous states of the program. Yep. Yeah. So that is the goal, and I feel like I'm pretty close here, and it's pretty exciting. So yeah. So the next step is like I'm gonna write a program to go in through this log, parse it, and then I'm gonna recreate all of the objects. Like whereas in my previous time travel debugger code, I actually had the programming language itself be immutable, right? I had I built my own programming language, and in the language, when it's running, all the data structures are immutable. Well, it was pretty impractical to make Python do that. So and I kind of changed my mind about that because I do want it to work for the mainstream programming languages, and that's not going to be practical to change a mainstream language to do that. So I'm just going to have it log, and then I reconstruct all the past state based on the log.
Reconstruct the past state. Okay, so you have the log, and then you based on the log, you are going to write a program to parse the log, and then you are going to create, say, the object on the log. At that time, that's gonna be immutable, right?
Yeah, I think I'm gonna recreate all historical states by using immutable data structures.
Okay.
So it'll be something like, I'll put our picture on the side here. It'll be something like, this is, by the way, I was inspired to do this after I learned about something called operational transform, which is a technique that's used by collaborative editing systems such as Google Docs. So in Google Docs, have multiple people editing the same document at the same time, and but each user has their own current version of the document, right? Like, I don't have that problem here. I just you have like a Google server, and then like there's 2 users editing a Google Doc, right? So when a user edits a Google Doc, what Google Doc does is it uses something called OT, which is short for operational transform. And what it does is actually when you add some text, this is captured as a command that gets executed on the document basically, and then that command gets sent to the server. I meant for this to be server. That command gets sent to the server and it gets blasted to the other client. So the other client is like, oh, I got a command that says add hello here at this position. But if this client at the same time had a conflicting command, like the user also wanted to add hi here.
Right.
What that does is there's a transformation. If the two commands happen to be conflicting, there's a transformation procedure that will transform this add hi in a way that works with this add hello command.
Okay.
How should I describe it? So it'll be like, okay, the server told me I have to add this hello, but because the add hello has higher precedence than my add hi, then I need to add hi after the hello. So what I'm gonna do is sort of after this add hello, I'm gonna put my add hi after the add hello. And what that means is I'm gonna shift the index of the insertion over by 5 to make the hi go after the hello.
Oh, I see.
So there's some intelligence in the algorithm to sort of resolve these conflicts automatically by saying, well, if the hello takes higher precedence than the hi, then I should shift the hi over to after the hello has been inserted.
So it's kind of like a queue, right? You have different comments, different commands coming from the server, and then you put them in a queue. And then you also put your local in the queue as well. And then there is a certain algorithm that's like, okay, the two things are at the same time, then I do this to resolve the conflict.
Yeah, but the conflict doesn't have to be solved at the server. The conflict can be resolved at each client computer.
Right, the server just stores each event, and then the client can take the event and do whatever he wants.
Yeah, but I don't have that problem in my scenario because I don't have multiple users of my same runtime. But what I took away from that is that, I don't have to do this immutable data structure during runtime. I can just reconstruct it and look at each operation that the Python interpreter does as a command. And then based on that command, I will transform the state in a certain way. Right?
Gotcha.
So for example, if I have this, if I have this push stack. Wait, where is the push stack? Push frame, I mean. If I have a push frame, that means I'm gonna make, initially, I'm gonna have an empty stack in my stack. Initially, that's empty. But if I have a push frame, I can interpret that as I have a push frame command that's coming in, and then I'm gonna have a frame on my stack now. Right. But I can perform this in an immutable way if I right. So I'm basically So basically, I'm gonna rebuild all the immutable structures that I would have had if the language was immutable in the first place, and then as I go, I'm gonna store each one of these immutable data structures into the database, the same way that I did before, and then my Zoom debugger can work off of that and display this Zoom interface and everything. Yep, that's the plan. I just want to tell you about that. Yeah.
Yeah, that's yeah, when the stuff can work with like real language, so that you can test it in like a program that's written in like the mainstream language. I think that's really, really nice.
Yeah, hope that works. I hope that